Work, also referred to as capital U, is done when a force causes movement or displacement of an object in the direction of the force. Consider a particle p having mass m. Let r be the position of p with respect to reference frame e. And the particle might be moving, so it will start at time t1. Suppose also that a force F is acting on P, and P moves along a path S of t to a new position at t2. To find the magnitude of the work done by the force, we can use the formula du equals F dot dr. Using the definition of the dot product, we can say that du, the instantaneous change in work, equals the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Recall that the dot product is commutative, therefore work can be viewed in one of two ways. Either as the product of the magnitude of the force and the component of the displacement in the direction of the force, or as the product of the magnitude of the displacement and the component of the force in the direction of the displacement. Work is always a scalar quantity, but be careful. Even though it does not have direction, work is considered positive if it works in the direction of motion and negative if it opposes the motion. Work has units of joules or Newton meters in the SI system and foot-pounds in the US customary system. The magnitude of the work done by a force over a time interval is the integral of F dot dr from the position at time 1 to the position at time 2. If F is constant, then you can pull that term out of the integral, and the magnitude of the work done becomes F dot dr. We will work specifically with gravity, springs, friction, and the normal force. So I will quickly introduce each of these and describe how to compute the magnitude of each. Let's start with gravity. We're told that gravity is a constant force acting on particle p, such that F equals negative mg Ey. We're asked to find the work done on particle p over the time interval from t1 to t2. I'm going to start by defining the vector r to be x of t ex plus y of t ey. Then recall that we said if a force was constant, then the work it does is F dot delta r. Then substitute values of x and y in for r. Note that the dot product of any two perpendicular vectors is 0, so ey dot ex is 0. You can think of this as the magnitude of ey times the magnitude of ex times the cosine of the angle between them, which is 90 degrees. And we're left with quantities in the ey direction only, including the distance traveled in the vertical direction. Then note that the dot product of any two parallel vectors is 1 because the angle between them is 0 degrees, and the cosine of 0 is 1. Therefore, the work done by gravity is negative mg delta y. We're used to the negative sign indicating a negative direction, such as the force due to gravity being directed in the negative Ey direction. However, recall that a negative sign for work indicates that the force is opposing the motion. In this case, the particle moved a distance delta y in the positive vertical direction, and the work done by gravity is opposing it, so that is why the work is negative. If the particle had moved downward, then the work due to gravity would have been positive. Now let's think about the work of a spring. Recall that the magnitude of the spring force is K times S, where K is the spring stiffness measured as a force per unit length, and S is the stretch or compression defined as the difference between the deformed length L and the undeformed length L naught. To help us visualize the spring force, let's draw a free body diagram. I will go ahead and add the weight force and the normal force. Be careful with the direction of the spring force. Remember that it will oppose the stretched length. So if the spring is stretched to the right, the spring force will be directed toward the left. Now let's go back to the general expression for work, which is du equals F dot dr. Unlike gravity, the spring force is not constant. It varies with S. So plug in the expression for the force and we get du equals negative ks E1 dot ds E1. And we can take the dot product of the E1 terms and set up the integral. And we find that the work done by a spring is negative 1/2 ks2 squared plus 1/2 ks1 squared. When working with springs, be careful with the sign and remember that a spring force will always act to return the spring to its undeformed length. Now we'll look at friction. Consider this block P sliding along a surface. We'll define the vector r to be the position of P with respect to an inertial reference frame, and v to be the velocity of P as seen from the inertial reference frame. We already know that the magnitude of the friction force is F sub F equals mu Fn. To find the work done by friction, start with a general expression, F dot dr, then plug in the expression for the friction force. We can assume that the motion is occurring only in the EX direction, but we need to remember that the friction force always acts in the direction opposite that of the motion, so we need a negative sign in front of the mu Fn term. Next, we can take the dot product and set up the integral. And the expression for the work done by friction is negative mu Fn times the quantity R2 minus R1, the normal force. The normal force never actually does any work. To understand why that is, consider particle P moving on surface S, which is fixed in the inertial reference frame E. Since the normal force is always perpendicular to the surface and the motion is always tangent to the surface, then the force and displacement vectors are always perpendicular. Hence, the work done by any normal force is 0. Let's do an example incorporating a number of forces. It seems complicated, but we'll break it down so it won't be that bad. Here we have an 8-kilogram block that is connected to a wall with a spring. Initially, the spring is compressed, but then a force is applied and the spring stretches. We're asked to determine the total work done by the block, assuming the slope is smooth. We know we'll need our expressions for the work done by a force. We also know that we'll need to work with the spring's compressed and stretched displacements. So I will add an inertial reference frame fixed at the unstretched length of the spring. We will also need to know the spring's displacement in the EX and EY directions. We know it starts with a 0.2 meter compression and ends with a 0.6 meter stretch for a total displacement of 0.8 meters. We can write an expression for this displacement, but it will help to draw a diagram. This should help us see that the block moves 0.8 cosine 40 EX minus 0.8 sine 40 degrees EY in meters. A free body diagram might also help us understand the forces. So I will add the weight and the normal force and the spring force and the applied force. Now let's compute the work done by each force. Starting with gravity, we know that the work done is negative mg delta y. If we plug in values, we have negative 8 kilograms times 9.81 meters per second times delta y, which is negative 8 sine 40 degrees in meters. Doing the calculation gives us positive 40.36 kilogram meters squared per second squared, which converts to joules. Note that even though gravity is directed in the negative EY direction, in this case, gravity is working in the direction of vertical motion, so its sign is positive. For the spring, we start with a known expression, then plug in values. Here, we know that K is 300 newtons per meter. The final position of the block is 0.6 meters, and the initial position of the block is negative 0.2 meters. It might be bothering you that we're not working in the EX or EY directions here. If so, recall that the work done is a scalar that depends on the displacement in the direction of the force. Since the displacement is aligned with the force vector in the case of the spring, we don't need to worry about the horizontal and vertical directions. And we find that the work done by the spring is 48 joules and it opposes the direction of motion. Finally, we'll consider the applied force. The angle makes this one a bit tricky, so let's draw a diagram. If the applied force makes an angle of 15 degrees with the vertical and the incline makes an angle of 40 degrees with the horizontal, then the angle between the force and the direction of motion must be 90 degrees minus 15 minus 40, which is 35 degrees. Moreover, since du equals F dot dr and the applied force is constant, then the work done is the magnitude of the force times the magnitude of delta r times cosine theta. Then we can compute this value by taking the magnitude of the force, which is 400 newtons, times the displacement, which is 0.8 meters, times the cosine of 35 degrees. This gives us an answer of 262.1 joules. Then the total work done on the block is just the sum of the work done, which is 254.5 joules.